Hello, Neve. Morning, Alicia. Hello, G-Man. Hello, Colby. Welcome, Abret. Hello, Lucia. Hi, Sarah. Hello, Deborah. Hi, Elena. I think that's everybody. Who just popped in? Hello, Arya. Hello, Dewa. Hello, Yusuf. Morning, you. Hello, Nav. Welcome, everybody. That you have to, for each question that you missed, you need to identify what your mistake was, work the problem correctly, and identify the correct physics or the correct mathematics that is necessary in order to answer that question. All right. If you made a stupid mistake, I'm sorry. It's not okay to just say I made a stupid mistake. I understand that stupid mistakes happen, but you need to identify why it's a stupid mistake. Why is it that that's not allowed? Okay. I know. I'll probably go to the grocery store. So that needs to happen. If you didn't get to a question, then maybe what you put for your mistake is I spent too much time on question 3B and therefore I ran out of time. I need to try to manage my time a little bit better. And then go through, work the problem, and write out in words the correct physics principles that allow you to do that. And that's basically their analysis. I have posted on in the course documents section example of a multiple choice and a free response. Both of them I do slightly different just to show you that there's not really a right or wrong format as long as you do those three things. Identify what was wrong with the physics, fix it, and then explain what the correct physics principles are. Lucia, question.
I had a question about number 6 on the multiple choice, I think. The one about accuracy and precision.
Yeah.
I was confused as to how we would be able to tell if it was accurate or not without having a known value.
Well, the big thing there in this specific scenario, I don't remember here. Let me look it up so I can see. I remember writing the question, but I don't remember exactly what the scenario was. Give me just a second to get out of my big view here. All right. The one about the position versus time graph, right? A ball rolling down a ramp, the ball starts at rest, distance traveled is plotted. Okay, you should be able to tell by looking at that graph that it's a quadratic, right? And if not, then you know the physics should help you understand that it's a quadratic as it accelerates down the ramp. What would happen if you drew in a quadratic curve there, going from the top, curving all the way down to the bottom? Okay, my issue with that and the reason why it's not considered accurate is because where should it cross the x-axis? Or where should it cross the y-axis?
At 0?
At 0 time, it should have 0 position, right? Everything else in the graph is really nice, right? The graph is almost a perfect quadratic curve, which means that they're being very precise and getting good numbers, except for the fact that for some reason the whole graph is higher than it should be. That can happen due to accuracy of measuring times using a timer. That can happen if we're using a ruler incorrectly. Parallax, if we look at it at an angle instead of straight up, it can cause things to change. So that's an accuracy issue. Yeah, so that's really why recognizing that the values, that's the only way that we can say, well, the values aren't what they should be, because everything looks really good, but it's not going through at least the 1 point that we know it should be. The precision, I guess, is possibly debatable, but I don't know that there's anybody that said it wasn't precise and wasn't accurate. If you did, and you've got a good reason for that, let me know. I'm willing to argue with you on that and possibly give the point back if you said not accurate and not precise. Okay, so you guys can chat with me later about that if you want. So here's what happens. You do your error analysis. You turn it in to me. I'll create something on the classroom where you can submit your error analysis. Please don't put it on the celebration. I won't see it there. I'll create a new assignment for it. You turn it in. I give you back 50% of the points. Okay, half of the points that you lost, I give you back. That's your AP adjustment. Okay, which fits fairly well with how the AP scores work. Okay, AP scores 50 to 60% is normally a 3, which should be, you know, your 70% passing there. And so I feel like that's a pretty good adjustment there. Same thing, you know, getting about an 80% is worthy of a 5, you know, an A. So that's how we'll work it. I don't mind doing reassessments. If all of your homework was complete and correct, I'm going to go through and look at that and just kind of double check it. I've already started doing it for physics, but I haven't done it for the AP classes yet. If your homework is correct and complete and you've checked it and everything's clear, then you can actually reassess if you want. What you have to do for that basically is the error analysis. You have to set up a time with me to discuss your error analysis so that we can actually have some one-on-one. I can make sure that I'm comfortable with you reassessing that you're going to do better the second time around. And then I'll let you reassess. We can set a reassessment date. Usually I say, you know, sometime within about 2 weeks. If anybody is interested in doing that, just flat out reassessing to replace the original score, please let me know. If nobody wants to do that, then I'm not going to set a date and I'm not going to write a reassessment. Another thing that I'm willing to do, since this is our first one, and I understand that the first time you get an AP physics test can be somewhat daunting and somewhat surprising as you're trying to figure out what you need to study and what you need to look at and in what depth and all those other things, is that our next assessment will cover Newton's laws, essentially, but it's very, very common for the Newton's laws to be connected with the kinematics, the free fall, all of that stuff. And it's very common to have a dynamics question that may have something with the experimentation and accuracy, precision, stuff like that. So I'm going to try to work all of that in to our next celebration. And so if you make sure that you get caught up on your homeworks and everything, I can just count that as a reassessment, but only for those that are caught up on their assignments. That would allow you to reassess without having to do an extra assignment, an extra assessment. So I'm open to that as well. Okay. Sarah, question.
I don't really remember if you went over this, but for question 10, since you said it didn't count, did you just take away, like, did you just make the test out of 28 or did you add a point for all of us?
No, I ended up just giving the point. So really you all got a free point. It doesn't affect the percentages that much. I decided that it wasn't worth messing with. So I gave everybody a point there. I hope nobody's too angry about that. If that is a problem, you can let me know. I will gladly take the point away and grade you out of 28 instead of 29. But it was my way of saying I'm sorry it was messed up. I'll give you the point for those that stressed out because of it or spent an extra minute or two on it. that was my way of saying sorry. So you just get the point. AP won't do that, by the way. They'll say sucks to be you. Other questions? Anything on the idea of reassessment or anything like that?
I have a question. Before you said that the passing grade is 70%, is it not 60?
Actually, I don't know what it is at this school. What is it at this school?
I think it's 60. I'm not sure how AP though.
I honestly have no idea. I don't think the AP is different than anything else, but I'm sorry, that's not something I've looked into since arriving at this school, but I've been at schools where it's different. So that's my current confusion. My last school didn't even use percentages. It was IB and you just got a 1 through 7 and that was it. So this is one of those scenarios where I'm open and I say, I have no idea what's going on right now. But if it's normally 60, then it's 60. Yeah. Which means technically you could get a 40% and pass if you do the error analysis, if passing is what you're hoping for. Because you got 40% error analysis extra. Yes, Deborah, sorry.
Is there a limit to how many error analyses we could do or reassessments?
You mean over the course of a semester or for a specific assessment? Just over the course of a semester? I'm not going to limit that. I don't think there's a good reason to limit that. There is a good reason because it's a lot of work on the teacher, but I don't think that that's necessarily the most beneficial thing to you guys. The purpose of this is hoping that it will benefit you. If you give me a piece of crap, I'm not giving you the points, so it won't benefit you. But yes, no, I'm not going to set up a limit. You can do it on each assessment, no problem. If you're willing to take the time to do it properly, I'm willing to write an assessment and grade it, or give you the points. Yeah. And it does mean more work for me, but if it means that you guys get something out of it, then so be it. Other questions? Sweetheart, can you take this because it's probably going to be here soon. They may contact you, but yeah, just hold on to that. It's probably like 5 minutes now. No other questions? Lovely. Okay. Then I think we're ready to move on. If you do come up with questions about that, just let me know. Again, the one thing that I would like to know, if anybody really is planning on just doing a separate reassessment for this specific celebration, please do let me know within the next day or two so I can plan a day and start thinking about writing the reassessment. Just so that you're aware, reassessments are not designed to be harder or easier. My hope is that they're at a similar level, but they will be completely different. The questions will be different. They're not just going to be changing a word or changing numbers. They will be completely different and try to attack the concepts from a different point of view. Yeah. Anyway, yes, Avery.
Usually, how long is the retake away from the test?
Usually I'll try to give you 2 weeks. 2 weeks I feel is long enough that you've had time to work through and fix any ideas that are kind of askew, but it's not so long that you're starting to forget things and I don't want it to interfere with our next assessment either, right? We want to be able to, when the next assessment comes, you know, we're able to not have to worry about doing multiple things at once. So I understand it takes time on you guys' end as well. Anybody else? Okay, awesome. Yeah, so if we did do it, I would likely do a date 765, like around the 18th, 19th, something like that. I usually try to do it after a weekend because I know that's when you guys have a little bit more time and you have the choice of studying a little bit more if you want to. That's not the date. I'm just saying that's probably about when it would be. Okay. Okie doke. If there is nothing else, and I don't see anybody else waving maniacally or quietly. Okay, looks good. We're gonna go ahead and move on then. We're gonna pick up with where we left off last class. And let me just get connected here. And we'll look at that. Do you have any questions? Oh, I did. Do you have any questions conceptual from last night's stuff? I know before I was asking about questions about the celebration. Is there any questions, ideas that you want to discuss from last night's? I will get up a key. I'm sorry, there's not one up right now, but we'll continue working on that. Nada. Okay. All right. Just thought I'd give you a chance. Okay. Here we go. All right. So we're going to pick up from where we left off. Last time we were looking at the free body diagrams, and so this time we're gonna start from there. My hope today is that we're gonna do some conceptual things, and we're also gonna work through a bunch of problems. We're just gonna get through as many concepts, as many problems as we can over the next hour plus a little bit. All right. Now, it looks like is my screen sharing for you guys? No, okay. Let us try this again then. Still no, huh? Oh, I know why. I was sharing it to AP Physics too. It was sharing, it just wasn't sharing with you. All right. Now I got it. Okay, sorry. Problem with working with multiple screens at once. Here we go. Lovely. We are ready to go. All right, so here's what I'd like you to do. On the concept test, CT, I am going to send you out into breakout rooms so that you have a minute, only a minute each time. You'll have a minute to chat it over with a partner. Okay, this one, there should not be a second ball on there. I'm actually not sure why there's a second bounce showing up. It was not there this morning. But yeah, so please ignore the second ball. So create a force diagram for a ball that is in that position. It's traveling upwards. It's not quite at the maximum yet. I just wanted to draw a force diagram for that. So I'm going to send you out into breakout rooms. You'll probably have 2 people in your group. You may have 3, but otherwise, for the most part, 2 people in a group. And you've got 1 minute to work through this and talk about it. I'll see you in a minute. All right, everybody's back. Let's see. Yusuf, what did you guys come up with? What did your force diagram look like?
So we were still like deciding, but so there'd be the force of gravity downwards,
Gravity downwards.
and then there would be the force of the motion, which would be at an angle to the right, like upwards.
Like this.
Yeah, something like that. We still didn't finish.
Okay, anything else?
There'd be the normal force. It should be, I think it should be perpendicular to the force of the motion, but we didn't finish.
Do you think something like this?
But I drew it upwards. So.
Upwards? Like that?
Yeah.
Okay. Awesome. Anybody else got the same thing or got something different?
Our group did something a little different.
Okay.
We said that if this was like when you throw a ball up in the air, then at that moment, the only force on it is the force of gravity that's acting on it like down. Yeah.
That's all you got?
Yeah.
Okay. Anybody got something the same or something different?
For our group, we decided that there would be gravity going downwards, and then would drag or air resistance.
Which
Going-
direction?
We were debating if it would go to the right or upwards, but we ended up making it go upwards, or yeah.
Like that? Or just straight up?
Yes, we decided straight up in the end. And then there's a normal force going to the right.
All right. I'm going to stop there. I think we got enough options, and my guess is that everybody has one of these or something somewhat similar to it. Okay, let me ask you all, what is touching the ball right now?
Air.
Air? Anything else?
The force of gravity.
Not touching.
Oh,
We'll get to that. You're correct. There is a force of gravity. I think everybody agreed on that much. I'm glad you all got gravity and the gravity's down. But is anything besides air touching it? Okay, so I'm glad that we had so many different ideas here, but is there anything touching it, pushing it up to the right? No, that is not a force right now. That force existed before, right? Down at the beginning when it was being launched, but right now there is not a force there. At this point in the arc, there is no force pushing it upwards. But wait, if there's no force pushing it upwards and gravity's pulling down, how in the heck is it going up?
Because there was a force pushing upwards, but no longer.
Yeah, that force gave it some upward motion, right? And Newton's first law says that it's going to keep doing what it's doing. It's going upwards because something made it earlier go upwards, and it's going to keep going upwards until something makes it stop, and then it'll turn around and come back the other direction. We don't need a force to keep going. Things just keep going. That's Newton's first law. All right. A couple of you guys mentioned a normal force. What is a normal force?
a force that acts perpendicular to the surface?
That's right. It is a contact force. A normal force is a contact force, which, as Lucia says, this is a sign for perpendicular to the surface. Is there a surface here? Is there any contact? Then, my friends, there ain't no normal force. Okay? The normal force is not this magical force that opposes gravity. No. The normal force is not Newton's third law. No. Remember, Newton's third law says that if gravity pulls down on the object has a gravitational force up on the earth. That has nothing to do with normal force. And I know this is a hard concept to get by because you have been told repeatedly forever that the normal force of the table opposes the gravity, and that's Newton's third law, and that is not correct. There is no normal force here. No normal force, no force of motion. Nothing is touching it except for the air. If you want to consider the air, you could say that there is some fluid friction. But friction, remember, friction opposes motion. What direction is the motion? The motion right now is up and to the right. Friction opposes that. If you want to add in friction, friction is going to be down to the left. It is causing the ball to slow down. It is opposing the motion. Right? Friction occurs when the molecules on the outside of the ball rub against the molecules of the air, and some of the energy of the ball gets transferred into the energy of the air. It's all about energy conservation. We haven't even talked about energy conservation yet, and we are going to talk about energy conservation because that is so important to physics in general, not just kinematics and dynamics, but we're going to talk about, if you go into later physics, you'll do thermodynamics, and conservation we'll do later this year, conservation of kinetic and potential energies. We'll do conservation of mass energy when you talk about E equals mc squared and particles being split apart and mass turning into energy. Energy has to be conserved. Energy doesn't disappear. It never goes away. It always goes somewhere. And so energy is going into the air. Friction is something that happens opposing the motion. All right. So what we've come up with here then is that your drawing can either look like this if you are ignoring air friction, or if you want to add air friction in, it would be doing this, going down and to the left, exactly opposite the direction of the motion of the ball. Questions? I got a lot of stuff. Any questions? And I can't see hands right now because I've got the screen shared and I can only see one person because I'm trying to record right now. So you can either hit the raise hand button or you can just unmute yourself and say "Mitta bawada," and then whatever your question is. Nothing? Okay. In that case, we're going to do number 4. Okay, you're going to get another minute. We're going to shuffle the rooms up a little bit. Just keep things interesting. All right, you've got 1 minute. Concept test number 4. You can see it on the screen right now. A ball rolls off the incline and off a horizontal ramp, ignoring air resistance. So this time it specifically says ignore air resistance. Draw a free body diagram of the ball as it moves through the air just after leaving the horizontal ramp. Okay, so you've got a ramp that goes down like this. The ball is going, and then it goes horizontally and it goes, right? So the question is, draw a free body diagram on the ball just after leaving the horizontal ramp. So it's right there. What are the forces on it? All right, you got 1 minute. Adios, chicos. do the cross-curricular thing. Spanish and physics at the same time.
It's true.
Bring it
He
on.
said that I go back wrong. I don't understand, I sent a message. Anyway. Because if he meant that I touch the middle line, that's because he asked me to go back some more. So we were on the left side of the road, but I went on the right. I really don't know what I did wrong.
Okay. Well, hopefully your teacher understands whatever's going on there, or like Nasser said, it could just be it was your first time, and that's what they do here. It very well could be that. No, eat whatever you want. I got 3 things because I figured that would be enough.
Okay.
It's some type of flat bread. It's the really thin flat one.
Is there something inside?
I don't know. One of them's supposed to have the masala. Sorry, my class is starting. Like they're back in the classroom. Sorry.
Hello?
All right.
I'm sad.
What you got? Let's see. Jimin, what'd you guys come up with?
I'm sad because I failed.
There's that there's a gravity.
Okay. Gravity.
Yeah, that was it.
That's it? All right. Anybody got something different?
Friction. The gravity and friction, so gravity downwards and then friction against the platform, so diagonal and to the right.
Like this?
No, I would say more like downward friction,
Downward friction?
like against the platform.
So which direction would the friction be pushing?
I guess.
Right, the motion, I think I understand what you're saying. Are you talking about up here?
Yeah.
So the motion is downwards, so which direction does the friction have to be?
Upwards.
Gotta oppose the motion, yeah.
Yeah.
Okay, so if you want to include, the problem here though, I will mention this though, is that it wants a free body diagram just after leaving the horizontal ramp.
Okay.
So we're not on the ramp anymore. So if anybody added anything before that, it's just here.
Okay.
If you were up on the ramp, then yes, you're right. There should be some type of friction pushing backwards. Okay. Anybody else? Anything different? Okay. Very good. This is our answer. That's the only force. It's not touching anything. There's no contact forces. If we're ignoring air resistance, then that's it. There's nothing touching it. Therefore, there can't be any other forces. Friction requires something touching, right? All the other forces that we have, other than electromagnetic, nuclear forces, things like that, which obviously aren't taking place here, they all require contact. All right, awesome. Let's take just a minute, talk about mass versus weight. We'll do an example and then we'll try a couple more. All right, so what is the difference between mass and weight? I mean, we know that something with big mass has big weight, but what's the difference? Anybody know?
Mass is a scalar and weight is a vector.
Okay, that's a good difference. Mass is a scalar, which means it doesn't have direction. It does have a value, but no direction. And weight is a vector. All right, awesome. I like that. I like that. What else?
Mass is how much matter makes up something, and weight is the pull of gravity on an object.
Okay, and I'm gonna adjust that slightly because if you say the pull, people might get confused between the acceleration and the force. So I'm gonna say the force of gravity, which I think is what you were saying on an object. Good. So, you know, I saw my wife showed me something a little while back. It was actually a couple of years ago. It was a meme on Instagram, and it was a meme for an instant weight loss program. And basically it was go to the moon. Right? So you have instant weight loss. Yes, your weight is now a sixth of what it was on Earth. Congratulations. However, your mass has not changed. If you go back to Earth, it's the weight's back, right? So when people talk about losing weight, it's not really about losing weight. It's about losing mass. It's the matter. It's how much stuff you're made of. That's what matters. Now, if you want to get technical about it, you don't really need to worry too much about this, but physics is now going in the direction that all matter is actually basically kind of the same. And what matters is how does that matter interact with the Higgs boson field? If you've ever heard of Higgs boson, that's basically what it is that the Higgs boson field interacts with particles and gives them what we call mass or inertia. And something that interacts in a way that makes it hard to move is something that has a high mass or a high inertia. But the thing that we need to know at this point is mass is just a scalar. It doesn't have direction, and it's just a measure of how much stuff you're made of. That's going to stay the same whether you're here on Earth, whether you're on the moon, whether you're in outer space. You can be weightless. You can have zero weight, and yet the mass is the same, which means, of course, that the inertia, many of you use the word of inertia, and we talked just in passing about this last time. Mass and inertia are the same. They are literally the same thing. We just use the two different words to explain the same thing. Okay? Weight is the force of gravity on an object. Now, to get the weight, usually what we do, we learned about the second law last class, which was F equals ma. So to find the force of gravity on an object, which is the weight, all we do is we take the object's mass and we multiply it by what the acceleration of gravity would have been if there were no other things affecting it, which is, in this class, we'll just consider it to be our negative 10 meters per second squared, or your negative 9.8. That's fine, either one. As I've mentioned before, AP is pretty flexible on which one you use there. Okay. Any questions about mass versus weight? All right, then we're going to do our first example of the day, which is this stoplight, which is hanging. It has a mass of 100 kilograms. And assuming that it's hanging in equilibrium, we want to find the tension in each of the three cables. All right, so here we go. The first thing we're going to do is we're going to draw a free body diagram on the light. Now, we're doing the light because we have some information about it. We really don't know much about the cables right now, but we can do a free body diagram on the light there. So what are the forces acting on that stoplight that's hanging? What are the actual forces on it?
Isn't there tension?
There's tension. Specifically, if you look closely, it's tension 3, right? It's this one right here. All right, what other forces are acting on my stoplight right now?
Gravity?
Force of gravity. Yeah, that guy is always around, isn't it? Notice that I drew my tension and my gravity approximately the same length. Are there any other forces acting on my stoplight right now? What about these guys? Do I need to attack? Are those part of it?
I don't think that affects the
Okay.
lights.
Why is that, Dewa?
They would affect the is that the third tension line? I can't really read it well.
Yeah, here, I can draw it a little bit bigger. The picture didn't show up as big as I thought it would. Yeah.
Yeah, but tension 1 and tension 2 would affect tension 3.
Right, but they're not touching the stoplight, are they?
Yeah.
And so since those are not touching the stoplight, then we don't include those in our force diagram for the stoplight. So Dewa is exactly correct. There's nothing else. It's not moving through the air, so there's no air friction. There's nothing else touching it, so there's no normal force. This is it. You got the force of tension pulling up and the force of gravity pulling down. Okay, so what we're gonna do is we're gonna write our formula like last night, where you were practicing, or what we were doing in last class, where we say the tension plus the force of gravity needs to equal the mass, which was given to us, that's 100, times the acceleration. Is my stoplight accelerating right now? Is it moving?
No.
It's not moving. It's not moving. The velocity is not changing. Therefore, my acceleration is 0. Okay. Now, we just talked about that we can get the force of gravity, right? The force of gravity is mass times the acceleration of gravity. So what we're going to do is go ahead and put that in. So we're going to say tension 3 plus the force of gravity, which is the mass, times g, which I'm going to just use negative 10 to keep it simple, equals 100 times 0, which of course is 0. I'm just going to go ahead and make that 0. No need to keep writing it. Okay, and you'll notice that I put a negative 10. Right? That's important because we recognize that the force of gravity is down. So in the end, I need to make sure that this force of gravity, yes, I'm adding it on, but it needs to be a negative number that's being added. So the negative 10 of the g is going to take care of that. Here we just solve. So we go T3 minus 1,000 is equal to 0. So we now know that tension 3 is 1,000, and the units for force are what we call newtons. Okay, newtons come from SI. So as long as you keep everything in meters and seconds and kilograms, which are our base SI units, then you will get newtons. If you use centimeters, if you use hours, then you don't get newtons. So always convert everything into meters, seconds, kilograms, so that you can end up with the correct units. All right. Questions about how we got tension 3? All right. Now we want to connect it to the other two, because the question actually says find the tension in each of the 3 cables. All right. So at this point, we need to connect that T3 to the T1 and T2. And this is what Dewa was talking about. He said, well, T3 is touching T1 and T2 at this point right here. So what we're gonna do is we're gonna draw a free body diagram on the connection there where all three of those wires are connected. All right, and so that point, there are three forces acting there, right? We've got tension 2 pulling up this way with an angle of 53. We've got tension 1 pulling up this way. I'm using alternate interior angles. How's that for some geometry? Alternate interior angle says 37 degrees. And then I've got T3, which is downward. And we do know that T3 is 1,000 newtons. That's what we found in the first part. Why am I not including gravity here? I mean, gravity is here. Why would I not include the force of gravity? Any ideas?
Because all the force is not coming from gravity, it's coming from the string that's pulling them.
Yeah,
Tension from the string.
Yeah, exactly. We're really focusing on the forces on this point, and this point isn't like an object, right? It's not like a ball that's sitting there at the connection of these wires. We're just considering that point in space where the wires all come into connection with each other. So really, there's not a mass there that's being pulled on. One of the things that we will say to simplify things in this physics course is that we will consider most of the time our ropes and our cables to be massless. Okay, we're living in this perfect physics world. We don't want to have to worry about all of those masses because that actually really complicates things if I have to consider the mass of all of those cables. And so what we're going to do, and this is consistent in all the problems, unless it says otherwise, it will almost always either tell you or ask you to assume that the strings or the cables have very little mass or negligible mass, or that we can ignore them, or that they are massless. Okay, this is just one of those things that we do to try to make the physics a little bit easier as we're trying to understand the principles of it. Okay, so we're not going to worry about any of the masses, any of the weights, just the tensions here. Okay, so perfect. We're moving on. In this case, we have 2 dimensions, right? And we mentioned this last class, is that if we have up and down and side to side, we can write 2 different equations. One for the horizontal pieces and one for the vertical pieces, right? So that's what I'm going to do. I'm actually going to break each of these vectors into a horizontal piece and a vertical piece. So this is T2 in the X direction, and this is T2 in the Y direction. And then this is T1 in the X direction and T2 in the Y direction. T1 in the Y direction. So if I do an equation for the horizontal forces, the only horizontal forces there are T1 of X and T2 of X. And that is the sum of the forces, which needs to equal MA, but the object isn't moving. We talked about that before, so the MA should be 0. There's no acceleration there. So T1 plus T2 equals 0. I can also do the vertical ones, right? So we go T1 in the Y direction plus T2 in the Y direction plus T3, that's vertical as well, and it's downwards. So I'm going to put a negative 1,000 there because it's downwards, and that should equal 0. We're really close to getting to the point where we can solve this now. This is actually probably one of the most complex problems mathematically, the physics isn't too bad. We're just talking about balancing the forces, but the math can get pretty tough here. What we're going to do for each of these components is we're going to write it in terms of the original tension. Okay, because what we really want is T1 and T2. I don't really care about the horizontal component and the vertical component. I eventually want to get T1. Okay, so hopefully what you can see is if I'm looking at, for example, T1 of X, right? That is related by a trig function with the angle here. So if I'm looking at T1, that's the adjacent side. So the cosine of 37 is equal to the adjacent over the hypotenuse, just like that. Which if I multiply both sides by T1 means that the horizontal component is just T1 cosine of 37. I can do the same thing for the vertical side now. Right? Except the vertical side is the opposite side. So that's going to be sine. It's going to be sine of 37 is equal to T1y over T1. That should then give us that T1y is equal to T1 sine of 37 if we work it out. Questions so far? I want to make sure, I know it's a long process. I want to make sure I'm not losing anybody in each step. We'll do lots more examples, but each step needs to make sense. We'll do lots of examples so we get used to putting all of them together. Questions? All right, we're going to do the same thing for tension 2 now, right? So tension 2x, I can do cosine of 53, which is going to equal the adjacent T2x over the hypotenuse, which was T2. It's a lot of work with variables. So again, T2 cosine 53 is the horizontal component. This is why it was so important that we do vectors early on. We understand how to break them into components. Break it into that horizontal piece and that vertical piece. We should be able to do the same thing to get T2 sine of 53 is equal to T2 in the y direction, right? That's the opposite over the hypotenuse. So now that we have functions for each of these, we can go ahead and put it into the functions that we've already written here. Okay, if we do the first one here, we've got T1x, which is T1 cosine 37, plus T2x, which is this guy right here, T2 cosine 53, that should equal 0. And then I'm doing the same thing for my second equation here. T1y right here is T1 sine 37 plus T2y, which is T2 sine 53. And then it'll be running out of space here. Minus 1,000 equals 0. So we've substituted each of those components in so that it's in terms of T1 and T2, which is the total tension, right? But then by multiplying by the trig function, it gives us the horizontal components. It's supposed to be a 0. And it gives us the vertical components. At this point, you see you have two equations, and there's only two variables. You can solve that. You can solve it through substitution. You can solve it through elimination. You can solve it using your fancy smancy calculator, right? Your calculator is able to solve that. If you're more comfortable with Desmos, you can use Desmos for now. But you really do want to learn how to do it on your calculator because you're not going to have Desmos on the AP exam. You are going to have your calculator. So I'm going to give you just a minute to do the math part. There's no physics left. Okay, this is all math at this point. So I'm going to give you a minute, figure out how to get that into your calculator or your Desmos or substitution or elimination by hand if that's the method that you prefer. But if you prefer that, I think you're crazy. But see if you can figure that out using either your calculator or possibly Desmos.
So right now, we're just calculating cosine 37 plus cosine 53.
You can put those numbers in. That'll give you the coefficients of T1 and T2. Yeah. It's simultaneous equations, right? It's like when you had in math class, when you had like a 3x plus 4y equals 7, and then negative 2x plus 5y equals 16. And you learned how to solve that by using substitution or elimination or graphing or plugging into your calculator. That's exactly what you have here, right? The cosine 37 is the number in front of your x, which is the T1. The cosine 53 is the number that's in front of your y, which is T2. So T1 is x, T2 is y. You have x and y there as well. These are just numbers. So yeah, you can punch those in, you can get those numbers, and then you need to use your calculator or use substitution like you learned in math class to solve for x and y. Do you guys know how to do that? Actually, is there anybody that does not have a graphing calculator? Hold on, I'm trying to make sure.
I have one in Oman, but I don't have one with me right now. So like I have to like look up stuff online. But like there's like online alternatives.
Yeah, so you've got Mathroom Alpha or Desmos or perfect. As long as you've got something that you can use. Okay, is there anybody else that doesn't have access to a efficient calculator? Okay, awesome. Is there anybody that doesn't know how to use your calculator to solve a system? I can't see everybody's faces right now, I'm sorry. But if you want to give me a no in the participants window if you have no idea how to use your graphing calculator to solve this.
Would you just, I'm asking, I'm not sure, do you just like plug in the two equations and then find where they intersect and find the x and y values?
That's one way to do it. Yep. I think there's actually a function on there that allows you to solve a system of equations, right? Yeah, If you go into, I was told most of you guys have this one. If you go into menu and you go to the one that is equation, it's letter A. So it's a little bit further down, but if you go to equation and you click on that, then the first option is F1 simultaneous. And so you can click simultaneous. You have two unknowns. So you hit F1 again and say I got two unknowns. And then it basically sets it up for you. Okay, so A is the number that's in front of the X, which you can actually, you don't even have to work it out. You can just type in cosine of 37 and it'll figure it out later. And then you put in the B, which is cosine of 53. And then the C is the number on the other side of the equal sign. So you're going to put 0. And then you should be able to do the same thing for the sine 37 and the sine of 53. The 1000, you got to move to the other side and make it 1000 first. So this is what it should look like. I don't know if you guys can see my thing right now.
Is there, can you do that on a TI-84 on one of these?
Yes, it is on there as well. If you go to, let me see it real quick. I don't have my TI-84 with me. It's at school. If you go to math, push math for me.
Yeah.
Oh, no, it's not in math on a 84. Is there like a program button? Yeah, program.
Okay.
Go down, there should be one called Polysmlt 2. PLYSMLT 2. It
No.
should be a program. Oh, no program?
No.
Try the catalog button.
Okay.
And then arrow down until you get to PLY. Is it there?
It's taking a while to get all the way down to P.
I know. Press the P button. There's a button that has a P on it above it. Just push that button. Does that take you down? No?
Yes.
Oh, lovely.
Where's the catalog button?
Over on the right.
Second 0.
Off 0.
Sorry?
Second 0.
Oh, I see it now. Thank you.
Yeah, sorry, it's one of those things above. I actually prefer the 84, but I was told nobody had it, so I don't have mine at home. I hope it's at school.
I forgot how to choose a second variable on the TI. So like
what?
I forgot how to choose a second variable. So I have the X, but I can't get the T variable because we need two variables first. I can't just use X for both.
Just a letter.
So I'm
just do alpha. Push the alpha button and then that letter.
Oh, okay, yeah, thank you.
Are we looking for PLY?
It should be PLYSMLT2 or something like that.
No.
No? Maybe you don't have it.
Maybe.
Okay, I don't know then. I'll have to, I was pretty sure it was in, for sure it should be in the catalog because that just lists everything your calculator can do. Let me see it one more time.
The catalog?
No, just the calculator.
Oh, okay.
I'm trying to remember the buttons. Lower it a little bit. Try doing green button and then the middle button up at the top, whatever that gray one is.
Just like on here, this one?
No, the ones at the top. The graphing buttons.
Yeah.
Yeah. So push the green button and then one of those. Sometimes that brings up a short list.
This brings me, it says like F1 and it does something like that.
Yeah, that's not the one we want. Okay, sorry. Yeah, for now, just graph it. I'll find out. I'll let you know. There is a way that you can just type it in like I did on the Casio, but it is a separate program. I'll have to find it. You know what, we missed something. I'm sorry. Our numbers are not gonna be right. We paid attention to the fact that the tension 3 was down, but we didn't do that up here in the horizontal one. Actually, it'll work. It's fine. It should be fine. Yeah, you should get T1 is negative 2183 and T2 is 2897. And the reason why you're getting T1 to be negative is that it's got to pull in the opposite direction. Because the horizontal T is to the left and the horizontal T2 is to the right.
What does the horizontal and vertical mean in the context of the tension problem?
Well, remember that the tensions, tension 1 and tension 2 were pulling in at an angle, but that doesn't work when it's really just a way to deal with the vectors, right? It doesn't really have a lot to do with the forces other than the fact that tension is a force and force is a vector, right? And so when we have a vector, we have to use vector addition. We have to pay attention to the direction that the vector is going. It's not as simple as saying tension 1 plus tension 2 equals tension 3, because they're pulling in opposite directions. Some of the force of tension 1 and tension 2 is not vertical. Some of the force that they're exerting is to the side. And so that's what we did in these equations over here to the side, is we said that the horizontal part of tension 1 and tension 2 have to be pulling equally in opposite directions, right? T1 horizontally and T2 horizontally have to add together to give me 0. And then we wrote a second equation saying that the vertical part of tension 1 and the vertical part of tension 2 have to add together to give me the vertical tension of 3. They have to balance out to give 0.
Mr. Bywater, for the
Yes.
second equation where you wrote T1y plus T2y plus negative 1,000, shouldn't T3 be negative? So then when you move it, like if you move that negative 1,000 over, you have it equal to a positive number,
Yes.
right? Because you have 1,000, but shouldn't T3 be negative? So it should be equal to a negative number.
It already is negative here. I put it in as a negative number because I knew it was downwards. Right? I already made it negative. It is negative.
But wouldn't it make sense to make it equal to negative 1,000?
No, because then T1 and T2 are both going to be negative, meaning that they're also going down. T1 and T2 have to be positive numbers. They should be.
Okay, because when you have it equal to positive 1,000, you get T1 and T2 being negative numbers. So I'm saying, like, if you move the negative 1,000 over by adding 1,000 to both sides, then you have negative values for T1 and T2.
They shouldn't be. Because two negative numbers won't add together to give a positive, right? T1 and T2 have to be positive. And then we have to add that to a negative to give us 0. Oh, yeah. Okay, so I do see we are going to have to do this. In the our problem, the answer that we're getting is a little messed up because the horizontal here, let's see. I really wish I was at school. This tension 1 right here, I'm making it green. Here, this one right here, that tension 1, we need to put it in as being negative. Why is it doing that? I need to put in as negative because it is to the left, right? Tension 1, the horizontal component, I even drew it in my picture here, is going over to the left. And so that value needs to be negative, whereas this one needs to be positive because that one's up. So if I go to my calculator and put in a negative there, instead of having a positive 0.798, and I hit solve, okay, this is what I get, and this actually is correct. You should get that tension 1 is 602, and tension 2 is 799. You should get two positive numbers for T1 and T2. That happens by when we do our simultaneous equations. This number right here needs to be negative because it's going to the left. We made this one negative like it should be. We made the negative 1000 because it was going down. But this one also needs to be negative because it's going to the left. That then is going to give us the correct numbers that we should have gotten in the first place. I apologize, I was not paying attention. All right, here's what I'd like to do. I think that spending too much time here is probably going to hurt us more than help us. What I want to do is we're going to skip a couple of the conceptual things. We'll go up to another problem and we'll see how it applies to a different problem. Okay. And maybe by working through another, I think if we work through another problem or two, that it'll help us to put some of the ideas together rather than continuing to beat this one down. The idea is you balance the forces, you draw a free body diagram, you balance the forces, balance the horizontal, balance the vertical. As we just found out, pay attention to the left, right, up, down. As you enter it in, make sure I entered in a negative force here because that should be tension 3. That should be tension 3 right there, which I put in as a negative number to show that it's going down. I had to make this one negative because this one here is clearly positive. So I needed the X to be in the left direction. So I put a negative on there. And then from there, the calculator should solve it. Okay. But like I say, let's take a step back. We've got 10 minutes left. Let's see if we can just skip up. We'll do another example. And so that we can get a feel and just say, yeah, we've got an idea of what's going on before we finish. Okay, and I think it'll be more valuable to look at more examples rather than beat the same one. Okay, so let's do this. Let's skip up to example number 2. Okay, a certain rope can handle 3,500 newtons of tension before breaking. If it's used to pull a 300 kilogram crate up with an acceleration of 2 meters per second squared, will it break or not? All right, let's draw a free body diagram. We're going to draw a free body diagram on the crate. So what are the forces acting on the crate? Nav, what forces you got? What are acting on the crate there? Nav, you with me? I'm afraid we lost Nav. let's see, you, what forces do you have on the crate?
Tension.
Tension, all right, so we got tension pulling up.
And
And, yeah, and gravity. And that's it. Nothing else is touching it, right? This is going to be it. You got tension up, force of gravity down. And the question is, am I able to achieve an acceleration of 2 meters per second squared? All right. Now, here's the thing. It does say that the rope can handle 3,500 newtons. And notice that there's a decimal there, so it's 4 significant figures. It says it can handle that, but it doesn't actually tell us that that's how much tension there is. So what we're going to try to find here is how much tension is there. If the tension is less than this number, then the rope can handle it. If the tension is more than that number, then the rope cannot handle it and it will break, because that's what it's capable of. So we've got our forces. Let's do our sum of the forces equals mass times acceleration. So we've got tension plus the force of gravity, which will equal the mass times the acceleration. And we can put some numbers in there. We're solving for the tension. The force of gravity is, remember, mass times acceleration of gravity. So I've got a mass of 300 times g, which we'll put in as -10. Notice that this will give me, when I multiply those together, it's going to give me a negative number. It's going to give me a negative force, which is what I expect because gravity is downwards. Equals the mass, which is 300, times the acceleration, which it's saying is 2 meters per second. And it does say that it's going upwards. So my acceleration needs to be positive because I've already identified down as being negative. So now I can calculate what the tension would be in the rope under these conditions, right? So we go T 10 times 300 would be -3,000. 300 times 2 is 600. Add it to the other side. And we get the tension equals 3,600. What does that mean about the rope?
It will break.
That's right. Because in order to get it up to that acceleration of 2 meters per second, it requires the rope to pull with this much force. But the rope can't withstand that much force. It can only withstand 3,500. If you've ever been fishing before, when you buy fishing line, I used to love going fishing. I did scouting and camping and fishing and stuff. And when you go fishing, you buy fishing line and the line says that it's 5-pound fishing line or 15-pound fishing line. And what that is it's telling you what tension that fishing line can handle. It's telling you how strong the cable is. A higher pound, it doesn't mean the line is that heavy. It means that's what the tension, what it's capable of. All right. Okay. Questions? I think that was a little bit easier. Hopefully that's helping put together a couple of the ideas. Hopefully we'll work through a couple more and it'll help us get some ideas, get the ideas down. Okay, we've got 4 minutes. Let's go ahead and look at this one. This is a classic. This is a classic Newton's law question. A guy on the floor of an elevator. Okay. You've all felt this. You're in the elevator and it starts moving upwards and you feel like you're being smashed into the floor, right? And then it gets up to the top and you feel like you're raising up just a little bit. You feel a little bit lighter as it gets to the top. You felt it, right? So let's figure this out. Several questions here. The first question is, can we find the force of reaction he experiences from the elevator floor when the elevator is standing still? All right, so free body diagram, force diagram. When the elevator is still, what are the forces? This is my man, because I want to know what the force is on the man. So what are the forces? You've got, sorry, in the interest of time, force of gravity. And this time, we do have a normal force of the floor, right? The floor is pushing up on him. There's contact between him and the floor. You'll notice that anytime I write normal force, I'm going to say what the normal force is from, because I want to make sure I'm not adding in any magical forces. I want to make sure I know this is a contact force with the floor. I've included that contact force, and I'm recognizing that that is a normal force. There's not really the normal force. It's a normal force. You could have 20 normal forces at the same time. It's just a force, a contact force. All right. So here's the man. He's got force normal up, force of gravity down. Our sum of the forces is going to be the normal force plus the force of gravity, which should equal mass times acceleration. Of course, if the elevator is standing still, the acceleration is 0. So then I'll go the normal force, normal force of the ground plus the force of gravity. It says it's a 70 kilogram man times acceleration, which is equal to 0. And you work that out and you should get that the normal force is 700 newtons. All right, 700 newtons. Questions about part A? Okay, what's changing in part B? Because we're not going to have time to work all the way through these. What's changing in part B?
The acceleration.
Is there acceleration?
It's speed, I guess.
Yes, very different, right? This says there's a constant speed. If there's a constant speed, what's the acceleration?
0.
0, yeah. So my acceleration there is going to be 0. And so I'm going to get exactly the same thing. You may or may not have noticed in the elevator, once you get moving to a constant speed, you don't feel like you're being pushed into the floor anymore. You don't feel any lighter. You actually feel somewhat normal. Okay, that's because once you get to a constant speed, the acceleration is 0, and the equation is going to look exactly like this. You're going to have the normal force, you're going to have gravity, you're going to have equals ma, the acceleration is 0, and if the acceleration is 0, you're going to get exactly the same thing, that the normal force is 700 newtons. The next one is going to change as it accelerates downwards. Okay, the picture is still the same, but now we have an acceleration downwards. All right, and the man's going to accelerate downwards at the same rate. So you're going to have the same exact thing. It's going to be the normal force plus your weight, but this time it's going to be equal to the man's mass times his acceleration, which now will be -4. That should be meters per second squared. And then you could solve that. Okay. You should get a smaller force. In fact, with these numbers, you should get 420 newtons. but I'll let you do the algebra. 420, not 42. Okay, notice that as long as you're paying attention to the negatives of the direction, acceleration down is negative acceleration, gravity down is a negative force. As long as we're paying attention to the positives and negatives, everything should work out because you're just adding the forces together to equal the mass times acceleration. Okay? And I know time's up, so I'm not going to say anything else. If you got questions, I'm glad to answer those. Otherwise, you are more than welcome to go. We'll continue working on this. We'll do a bunch more examples next time. Okay?
Bye, Mr. Bowe.
Thank you.
All right. Thanks, guys.